The previous section or previous session, you fellows would have discussed about the principle of potentiometer and what a potentiometer is. What is the need for using a potentiometer? That is the very first question that stands in front of us. Potentiometer is a device used to measure potential difference. You may raise a question. Already there is a device called voltmeter, then what is the necessity of using a potentiometer? I think it's quite simple. In the previous classes, you would have discussed about the measurement of internal resistance using voltmeter, measurement of potential difference using voltmeter, in which a voltmeter requires a feeble magnitude of current for its deflection, so that we cannot measure the exact potential difference or exact EMF of a cell using voltmeter. For example, if you go to a shop and you are buying a Elavarasu cell, then its EMF would have been mentioned as 1.5 volt. If you measure the EMF with the help of a voltmeter, you cannot get exactly the same value of EMF. Instead, you will be getting a lesser magnitude. If it is 1.5 volt mentioned, you will be measuring 1.46 volt or 1.45 volt, even 1.4 volt. Why it happens? It is because of this internal resistance of the cell. Moreover, when you use a voltmeter, it draws a feeble magnitude of current. Because of the flow of current, there exists an internal resistance in the cell, which makes a drop in voltage in the cell across the terminals of the cell, so that the voltmeter cannot measure the exact potential difference of the cell. Whereas in case of potentiometer, we will be measuring the exact potential difference across the terminals, or you will be measuring the exact EMF of a cell, because it requires no current for its deflection. You are going to measure the EMF or potential difference in zero currents. So for zero deflections only, you are going to measure the values of EMF and the potential difference. Now, we have to speak about what is internal resistance, because these are the terms which you discussed earlier. I would like to speak about it once again. When an electric current is made to flow through a circuit, the electrolyte of the cell offers certain amount of resistance to the flow of current when the current continues to flow from negative to positive terminal of the battery. So in order to have a continuity of flow of electric current, what will happen is that current starts flowing from positive terminal to negative terminal. After reaching the negative terminal, there should be a continuity, so that the current will be flowing throughout the circuit. So if the current has to flow from negative to positive terminal of the battery, it must pass through the electrolytes of the cell. So the electrolytes offer certain amount of resistance to the flow of current. It depends upon the time at which the cell has been prepared. If the cell is a old one, means the solution prepared is a old one, the internal resistance offered will be more. If the cell is a fresh one, the internal resistance offered will be less. It all depends, right? So this is about internal resistance of the cell. And we have to speak about the principle of potentiometer here. What is principle of potentiometer? The EMF of the cell is directly proportional to the balancing length of the potentiometer wire. The EMF of the cell is directly proportional to the balancing length of the potentiometer wire. So EMF is directly proportional to balancing length. That is the principle of potentiometer. That also was discussed in the previous section. And we can say here, EMF of the cell is directly proportional to balancing length. On what basis? In the previous section, we have studied when the jockey is moved over the potentiometer wire, at one particular point, the EMF of the cell and the potential difference across the balancing length of the potential difference across the balancing length of the potentiometer wire will be equal, so that no current flows through the galvanometer, no deflection is observed in the galvanometer. We used to call this a zero deflection condition, where we have obtained the balancing point. The EMF and the potential difference are balancing each other. Potential difference across the potentiometer wire and the EMF of the cell are balancing each other. Thus, we are measuring the amount of EMF existing between the terminals of the cell. So, you can easily measure the EMF of the cell using a potentiometer. Exact measurement of EMF is done with the help of potentiometer, not with a voltmeter. This is the standard 1 mark question. Which of the following device is more accurate in the measurement of EMF of the cell? It's potentiometer. Idea is very simple. Now we shall speak about the comparison of EMFs using potentiometer. This is also a simple idea. Actually, in the previous class also, you would have studied about the primary circuit, secondary circuit, and how the balancing has been done. The same thing is going to be followed here, but with a simple change made in the secondary circuit. Now, in order to have a clear picture, first you draw the diagram. The diagram itself gives out the entire description what you have to write, right? Comparison of EMFs using potentiometer. In this particular case, we are going to draw a diagram which explains the entire description. In order to compare the EMFs of two given cells, we have to construct a circuit as shown in the figure. Let me consider CD as a potentiometer wire. Let me make it bold so that you can see it clearly. Actually, CD be the potentiometer wire. CD be the potentiometer wire. A potentiometer wire is basically 10-meter long. And what is the need for having 10-meter long potentiometer wire? That we shall discuss afterwards. So CD is shown in one color. Now, the terminal C is connected to the positive terminal of a battery. The negative terminal of the battery is connected to a key. Let me say this is a key K or K1 you can have. And then we have a rheostat. And the other end is connected to the end D. And D is connected to the top terminal of the rheostat. We call this as RH. This is K1, and this is a battery DT. So the potentiometer wire CD is there. It is of 10 meter long. The end C is connected to the positive terminal of the battery. And the negative terminal of the battery is connected to the other end of the potentiometer wire D through a key K1 and a rheostat RH. This forms the primary circuit. This forms the primary circuit. Now, the end C is connected to the terminal M of the Dpdt switch. Terminal M of the Dpdt switch. What is the Dpdt switch called? Dpdt here refers to double pole, double throw. Or in other words, we can call it a 6-way. What is the need for using a Dpdt switch? Let me explain it. Maybe after completing the circuit. So the end M of a Dpdt switch is connected to the terminal C of the potentiometer wire. The N is connected to terminal N is connected to the jockey through a galvanometer and a high resistance. To a galvanometer and a high resistance. So this forms the secondary circuit. This circuit is not yet complete. This forms the secondary circuit. The terminals M and N of a Dpdt switch or a 6-way key is connected across these 2 points C and J. C is connected to M and N is connected to J through galvanometer and high resistance. And we can say the cells of EMFs whose value has to be determined must be connected across the terminals, let me say M1, N1. The cell of EMF E1 is connected across the terminals M1, N1, and the cell of EMF E2 is connected across the terminals M2, N2. M2, N2. So this forms the secondary circuit. This is the six-way key. Cell of EMF E1 is connected across M1, N1. The cell of EMF E2 is connected across the terminals M2, N2. Actually, this is the six-way key. This arrangement is called a six-way key. What is the need for using a six-way key? In the discussion for principle of potentiometer, you might have studied a cell of EMF E is connected across the secondary circuit and the jockey J is adjusted from its position. So that at one point, the galvanometer will show zero deflection, which indicates that the cell whose EMF and the balancing length are equal, so that they balance each other, so there is no deflection in the galvanometer. This is what you have seen in the principle of potentiometer. Now you are going to compare the EMFs of two given cells, for which you have to use two cells, cell of EMF E1, another cell of EMF E2. Each and every time while you are measuring the balancing length for a particular magnitude of current, you have to connect the cell of EMF E1 first, and then you have to remove it, then you have to connect the cell of EMF E2. In this way, while you are repeating the experiment for a set of readings, then you have to reconstruct the circuit 10 times for cell E1 5 times and another for another cell E2 5 times. So this will be a very hectic thing while doing an experiment or while performing an experiment. So in order to avoid this kind of trouble, we are introduced to this Dpdt switch or six-way key, where 6 terminals will be provided when and a key will be there at the point Mn. A key will be there at the point Mn. If you put the key over the terminals M1, N1, then the cell of EMF E1 will be included in the circuit. If you put the key over the terminals M2, N2, then the cell of EMF E2 will be included in the circuit. So while calculating the balancing length for a particular magnitude of current, you can use a Dpdt switch where it includes both the cells E1 and E2. You can use a cell at a time so that you can measure the balancing lengths very easily. So in order to avoid a kind of inconvenience, we are using a Dpdt switch. Idea is simple. So if you go through a textbook, you can understand it very clearly. The entire diagram gives you the entire description of this particular experiment. So a potentiometer wire CD is the ends of the potentiometer wire CD is considered. The terminal C is connected to the positive terminal of the battery. The negative terminal of the battery is connected to the key K1, and then the rheostat, and then the other end of the rheostat is connected to the terminal D of the potentiometer wire. This forms the primary circuit, and the secondary circuit is constructed using a six-way key, a galvanometer and high resistance, and then jockey. The terminal M of the six-way key is connected to the terminal C of the potentiometer wire, and the terminal N of the six-way key is connected to the jockey J through a galvanometer and a high resistance. And then the cells of EMF Z1 and E2, whose value, whose magnitude has to be determined, are connected across the terminals M1, N1, and M2, N2. Cell of EMF E1 is across M1, N1, and the cell of EMF E2 is connected across the terminals M2, N2, and this forms the secondary circuit. This arrangement forms the secondary circuit. Now we have to perform this experiment. Before going into that, just look at the diagram. The positive terminal of the battery, positive end of cell of EMF E1, the positive end of the cell of EMF E2 are all connected to the same terminal of the potentiometer wire C, which indicates that if this connection is done on this particular basis, if the battery, the cell of EMF E1, cell of EMF E2, whose positive terminals are connected to the terminal C of a potentiometer wire, then we can say the balancing length can be easily obtained. If you reverse the polarity of the cell of EMF E1 and E2, then you will never ever get the balancing point. So now to get the balancing length or balancing point on the potentiometer wire, the very first thing what you should know is the terminals of the battery in the primary circuit and the cells E1 and E2 in the second circuit, whose positive terminals must be connected to the same terminal of the potentiometer wire. Now it is clear here that the battery whose positive terminal, cell of EMS E1 and E2 whose positive terminals are all connected to the terminal C of the potentiometer wire. Now it is ready. This experimental arrangement, circuit arrangement is ready enough to determine the EMS of these two cells, and so that we can make a comparison between these two. Now, what we have to do in this particular case is that now you put the 6-way key over the terminal M1 N1. 6-way key over the terminal M1 N1. So what will happen? The terminal, we can say the terminal M1 N1 is connected now. Terminal M1 N1 is connected. So if you look at the diagram, what will happen? A current flow will take place. A current flow will take place, and it will happen like this. Or the circuit connection has been made like this. See, this is how the circuit will be completed. See, only one cell is included, another cell is excluded here. Now the key is put over the terminals M1 and N1, so that the cell of EMF E1 is included in the secondary circuit. Cell of EMF E2 is excluded in the secondary circuit. Now the jockey is moved over the potentiometer wire. Then at one particular point on the potentiometer wire, at one particular position of the jockey on the potentiometer wire, the galvanometer shows zero deflection. The galvanometer shows zero deflection, which indicates that the potential difference across this CJ, potential difference across CJ is now equal to the EMF of the cell E1. EMF of the cell E1. So by the principle of potentiometer, I can write E1 is equal to IR L1, where I is the current flowing through the primary circuit. I is the current flowing through the primary circuit. What is R? What is R? R is the resistance per unit length of the potentiometer wire. R is the resistance per unit length of the potentiometer wire. This is very important, must be mentioned. Small r is the resistance per unit length of the potentiometer wire. So small r, the resistance per unit length of the potentiometer wire, and the current flowing through the circuit for a given position of the rheostat. Current and the small r can be taken a constant. So I can write E1 is directly proportional to L1. Let me consider this as the equation number 1. Now, what we have to do is that we have to remove the key from the terminals M1 and N1, and then you have to put it over the terminals M2, M2, so that the cell of E2 will be included in the secondary circuit. E1 will be excluded. E1 will be excluded. Now we can show it with the diagram. Oh, I can show you the diagram. This is the terminal M, and this is the terminal N. Z1, N1, M1. Fine. Now the cell of EMF E2 must be included in the secondary circuit. So we can connect it like this. The key put over the terminals M2 M2, so that now the path will be completed like this. So what happens here is that the cell of EMF E2 is included in the secondary circuit. E1 is excluded. Now the same thing has to be done. What we have to do is we have to adjust the position of the jockey over the potentiometer wire, so that at one particular position of the jockey on the potentiometer wire, the galvanometer shows zero deflection, which indicates that the potential difference across Cj, potential difference across Cj is now equal to the EMF of the cell E2 is now equal to the EMF of the cell E2. Once again by principle of potentiometer, I can write the condition. That E2 is proportional to R. I can write E2 is equal to IR L2. As I mentioned earlier, I is the current flowing through the primary circuit. R is the resistance per unit length of the potentiometer wire. And we can simply say here, the EMF of the cell E2 is now directly proportional to the balancing length L2. Now we are trying to compare the EMFs of the two cells. So divide equation 1 by 2, so that you will get E1 divided by E2 will be equal to L1 divided by L2. Now, if cell of EMF, any cell of EMF, E1 or E2, either E1 or E2 is known, and the balancing lengths L1 and L2 are known, then you can easily determine the EMF of the other cell. So E1 can be calculated by knowing E2, L1 and L2. E2 can be calculated by knowing E1, L2 and L1. So idea is simple. E1 equals E2 into L1 by L2. E1 equals or E2 equals E1 into L2 divided by L1. So if any one of the EMF of the cell is known, the EMF of the other cell can be easily determined with the help of this potentiometer. And by adjusting the position of the rheostat, we can vary the amount of current flowing through the primary circuit. So for different values of currents in the primary circuit, you can repeat this experiment. You can repeat this experiment to determine the comparison of EMFs or to compare the EMF of the two cells. You'll be getting the same result. So if the current varies, correspondingly the value will be changing. Once again, and see, if the current varies, we can simply say here we are bringing out result here. E1 is proportional to L1 and E2 is proportional to L2. For the same current, EMF of the cell is directly proportional to the balancing length of the potentiometer wire. So if you vary the value of current, the balancing length will also increase. If the current is increased, if the current is decreased, the balancing length will also decrease. But anyhow, when you compare the EMF, once again you will be getting the same result. E1 by E2 equals L1 divided by L2. Apart from the experimental errors, apart from the manual errors, the result will be the same. Whatever the current provided in the primary circuit, ratio of EMFs of the two cells will have the same value. Thus, we can compare the EMFs of the two given cells using potentiometer. So idea is quite simple. If you look at the diagram, or if you look at the entire content what we discussed so far, idea will be very simple. If you look at the diagram, primary circuit is made of battery, key, and rheostat. They are connected to the ends of the terminals of the potentiometer CD, and then cells of EMF E1 and E2 whose EMFs have to be determined are connected with the help of Dpdt switch. So the terminal M of the Dpdt switch is connected to the end C of the potentiometer wire, and the end N of the Dpdt switch is connected to the jacky J through galvanometer and high resistance. The cell of EMF E1 is connected across the terminals M1, N1, and the cell of EMF E2 is connected across the terminals M2, N2. So this arrangement forms the secondary circuit. By including the cell of EMF E1, we are finding out the balancing length of the potentiometer wire, and then by the principle of potentiometer, we can write E1 is equal to IRL1, where R is the resistance per unit length of the potentiometer wire, and I is the current flowing through the primary circuit. So E1 is directly proportional to L1. For the same current, see, for the same current, you are now including the cell of EMF E2 in the secondary circuit, and by the principle of potentiometer, you can get the balancing length of the potentiometer, and by the principle of potentiometer, we can write E2 equals IR L2. So E2 is directly proportional to L2. So when you compare when you take the ratio of these two EMFs, you can compare the EMFs of the two given cells, where E1 by E2 equals L1 by L2, and E1 is equal to E2 into L1 by L2. or E2 equals E1 into L2 divided by L1. Balancing lengths are known. If any cell whose EMF is known, the EMF of the other cell can be easily determined. This is all about the comparison of EMFs using potentiometer. We can solve some problems related to it after completing the other heading. Now we shall get into the next heading. Which is the determination of internal resistance or measurement of internal resistance of a cell by potentiometer. Measurement of internal resistance of a cell by potentiometer. We shall discuss about that. We shall now speak about measurement of internal resistance of the cell. Already you have studied the measurement of internal resistance of the cell using voltmeter. Now we are going to determine or measure the internal resistance of the cell using potentiometer. Measurement of internal resistance of a cell using potentiometer. We shall discuss about this. Once again, we have to construct a circuit to measure the internal resistance of the cell using potentiometer. So first let us construct the circuit and then we shall discuss how to measure the internal resistance of the cell. Now, you consider the potentiometer wire, same potentiometer wire CD. The end C of the potentiometer wire is connected to the positive terminal of the battery. Negative terminal of the battery is connected to a key. Circuit may not have a rheostat, but you can keep it, no problem. The circuit has been given in your text. I'm just including a rheostat. There is no harm in including a rheostat. So a battery, a key K1, and a rheostat RH, which are connected across the terminals of a potentiometer wire, forms the primary circuit. This forms the primary circuit. The positive terminal of the battery is connected to the terminal C of the potentiometer wire, and the negative terminal of the battery is connected to the terminal D of the potentiometer wire through a key K1 and a rheostat. Through a key K1 and the rheostat. Now, the terminal C is now connected to a cell of EMF E. So the positive terminal of the cell of EMF E is connected to the terminal C of the potentiometer wire, and we can say the negative terminal of the cell of EMF E is connected to the jockey through a galvanometer and a high resistance. Through the galvanometer and a high resistance. A high resistance is always connected to the jockey before you connect the galvanometer to the jockey, because the galvanometer has to be safeguarded from the sudden passage of current from a potentiometer circuit, so that the galvanometer will get damaged. Now, to avoid the damaging effects of the galvanometer, we are introducing a high resistance in front of the galvanometer, and it is connected to the jockey chip. So, cell of EMF E, whose positive end is connected to the terminal C of the potentiometer wire, and the negative end of the cell of EMF E is connected to the jockey J through the galvanometer and high resistance. So this forms the secondary circuit. But if you leave this cell of EMF E like this, then the circuit will behave as a open circuit, and we can complete the circuit once again. Resistance box. We used to call this as a resistance box. A resistance box is the one in which you can vary the value of resistance by rotating the knob provided to the resistance box. So R is the resistance box, and another key, let me say here 2 is connected. along with the resistor R, and this resistor R and the key K2 are connected across the cell of EMF E. Connected across here refers to a parallel connection. Across refers to a parallel connection. So the resistance R and the key K2 are connected across the cell of EMF E. Now the entire arrangement forms the secondary circuit. So primary circuit has been explained, secondary circuit has been explained. How the internal resistance of the cell has been determined. Where we are speaking about the internal resistance. A cell of EMF V is connected in the secondary circuit. It has an internal resistance small r. It has an internal resistance small r. We are going to find out what is the internal resistance of the cell. What is the internal resistance of the cell? So in order to do that, you can just go step by step. First, is to remove the key K2. The key K2 is kept open. K2 is open. So R is not included in the circuit. R is not included in the circuit. R is not included in the circuit. Fine. If K2 is open, so R is not included in the circuit. So only the cell of EMF E is there in the second circuit. So the second circuit is like this: C, and then cell of EMF E, then galvanometer, then high resistance, then jockey. This is how the circuit is. This is a similar circuit which you discussed in the principle of potentiometer. So what you have to do is that we have to adjust the position of the jockey over the potentiometer wire. At one particular point on the potentiometer wire, the position of the jockey on the potentiometer wire, the galvanometer will show zero deflection. Galvanometer will show zero deflection. Now it indicates that the potential difference across the CJ, potential difference across the CJ and the cell of EMF E are equal and they are balancing each other. So the galvanometer shows zero deflection. And in this particular case, as the resistance R is not included in the circuit, this circuit now behaves as an open circuit. Now, in the first case, we can say the circuit behaves as an open circuit. So you are directly measuring the value of the EMF of the cell. So by principle of potentiometer, I can write E is directly proportional to, or E equals IRL1. E equals IRL1, from which I can write E is proportional to L1. Let me say this is the equation number 1, where I is the current flowing through the primary circuit. I can show it here. I is the current flowing through the primary circuit. R is the resistance per unit length of the wire. L1 is the balancing length of the potentiometer wire. So E is directly proportional to L1. So this is done by considering the secondary circuit as an open circuit. Because the terminals of the cell are not sending any current over here. So this arrangement behaves as an open circuit. Now you are including the key K2. So K2 is closed in the second case. K2 is closed. Resistance R is included in the circuit. R is included in the circuit. The cell of EMF E is there. Resistance R is there. K2 is there. Resistance R is there. This is how the circuit is. EMF E is there. So this sends a current along this path through the resistor R and through the key and then to the negative terminal. As there is internal resistance, it flows from negative to positive terminal so that the circuit will get completed. So when the key is closed, current begins to flow through the circuit. When the key is closed, the current begins to flow through the circuit. So the current will flow through the resistor, external resistor R, and also it flows through the internal resistance, smaller of the cell, smaller of the cell. So we cannot measure the EMF of the cell directly. Here, the circuit we can consider behaves as a what do you call a closed circuit. Here, the circuit behaves as a closed circuit. So the behavior of the circuit is closed. Circuit behaves as a closed circuit. So now, what is the amount of current flowing through the circuit? We shall speak about it. What is the amount of current flowing through the circuit? The cell EMF is sending, cell of EMF is sending the current, let me say I. What is the amount of current flowing through the circuit? Don't confuse yourself. Don't mess up yourself with this current and the current in the primary circuit. So the current flowing through the secondary circuit can be calculated as current equals EMF divided by resistance. As there are two resistances included in the circuit, I am writing I equals E divided by R plus R. So this is the current in the circuit. So what is the potential difference across the resistance R? What is the potential difference across the resistance R? Potential difference across the resistor R. This is the current I through the resistance R. So current through R is I equals E divided by R plus R. I equals E divided by R plus R. So current through resistor R is I equals E divided by R plus R. Potential difference across the resistance R can be written as V equals IR. I is E divided by R. I is we can say potential difference across the resistor R can be calculated. V equals IR. I equals E divided by R plus R. So I can write E divided by R plus small r into this capital R. For current, I have substituted this one from the earlier expression. So V equals E into R divided by R plus small r. So potential difference has been calculated. Now, when the jockey is moved over the potentiometer wire, see, you have to be very careful. While the key K2 is not closed, the circuit behaved as an open circuit. You have introduced the cell of EMF E alone, cell of EMF E alone. So we had EMF of the cell. In the first case, we had the EMF of the cell. So the balancing length, what we attained in the first case, is corresponding to the EMF of the cell. See, make it clear. You have introduced the cell of EMF E alone because the key K2 is open. So the potential difference across the balancing length of the potentiometer wire balanced the EMF of the cell. So you measured the EMF of the cell in the first case. In the second case, you have introduced the key K2 so that the path has been closed. The path has been closed. The resistor R has been included in the circuit. Now the cell has no longer its EMF. Now we have to speak about its potential difference. We have to speak about the potential difference across the terminals. It is no longer the EMF, and the potential difference across the terminal has been calculated here as V equals VR divided by R plus R. So just make it clear. First, you have balanced the potentiometer wire with the EMF of the cell. I am just drawing the secondary circuit alone. So this gives you the balancing length. This is for EMF. Now, in the second case, it is no longer EMF. Now we are speaking about the potential difference V, for which we are going to find out the balancing length. So in the first case, when key is open, K2 is open, and K2 is closed. When K2 is closed, we have introduced the resistor, external resistor R, so that the cell has no longer its EMF. Now we have to speak about its potential difference, and the value of potential difference has been measured as E equals CR divided by R plus R. Now when the jockey is adjusted in its position to get the balancing length, now we can say the potential difference is directly proportional to the balancing length L2. Potential difference is directly proportional to the balancing length L2. If we are clear with this particular idea, then solving problems will be very easy. In the first case, you have introduced the cell of EMF E alone. So, which means external resistance capital R is not coming into play. Now, in the second case, by closing the key K2, we are introducing the external resistance R in the circuit. So the cell whose EMF cannot be discussed here, instead, its potential difference have to be discussed. Potential difference of the cell has been considered. Only the potential difference of the cell must be considered. V is introduced. So V will be directly proportional to the balancing length L2 by adjusting the position of the jockey over the potentiometer wire. So when the potential difference is balanced on the potentiometer wire, the balancing length L2 will be obtained. So we can write ER divided by R plus R is equal to L2. R is directly proportional to L2. ER by R plus R is directly proportional to L2. Let me say this is the equation number 2, and then this is the equation number 1. E proportional to L1 is equation number 1, and the V proportional to L2 is equation number 2. Dividing 1 by 2, we will get E divided by ER divided by R plus R is equal to L1 divided by L2. L1 divided by L2. This E gets cancels out. Now we can take the R plus small r to the numerator, capital R will be there as it is. This is equal to L1 divided by L2. Now I can write this as 1 plus small r divided by capital R is equal to L1 divided by L2. Small r is required, so small r by capital R is equal to L1 by L2 minus 1. So small r is L1 by L2 minus 1 into capital R. So this is the expression for small r is equal to L1 by L2. Sorry. Small r is equal to L1 by L2. Small r equals L1 by L2 minus 1 into capital R. This will give you the internal resistance of the cell. So, in order to determine the internal resistance of the cell, the value of capital R, the external resistance connected to the secondary circuit, must be known. The balancing length L1, which corresponds to the EMF of the cell, must be known. The balancing length L2 corresponding to the potential difference across the terminals of the cell must be known. So if all these 3 quantities are known, the internal resistance R of the cell can be easily determined. So if the external resistance R, the balancing length L1 corresponding to the cell of EMF E. Once again, I can write here. This is the balancing length L1, which corresponds to the cell of EMF E. This is the balancing length, let me say L2. This corresponds to the potential difference of the cell. Why? In the first case, no external resistance is included. The second case, external resistance is included. So it is no longer EMF, it is potential difference, because internal resistance comes into play, which also opposes the flow of current. So there will be a voltage drop that will take place across the terminals of the cell. So we will not measure the EMF of the cell. Instead, we will be measuring the potential difference of the cell. Potential difference of the cell. I'll give you a clear picture over here. Once again, I would like to explain this. EMF of the cell, internal resistance R is there. As there is no flow of current taking place from the cell, there will be no voltage drop across the internal resistance of the cell. However, when an external resistance is connected, what will happen? The current flow begins to take place through the resistor R. As it reaches the negative terminal, the current must be continued by flowing from negative to positive terminal of the battery through the internal resistance R of the cell. So two resistances come into play. There will be a voltage drop V equals IR takes place across the external resistance, and V equals I into small r, which will take place across the internal resistance. Total EMF is the sum of I into capital R plus I into small r. So it is, if this voltage drop across the internal resistance is gone, then the potential difference across the cell alone will be existing, which is V equals E minus of I into small r. This you would have studied earlier. V equals E minus of I into small r. So it will no longer be EMF. Instead, it will be potential difference when the current begins to flow through the circuit. So L1 is the balancing length for the cell of EMF when the circuit is considered open. And L2 is the balancing length of the potentiometer corresponding to the potential difference of the cell. The circuit is closed. Now, based on this, we are bringing out the idea. See, idea is very simple. In the first case, EMF is directly proportional to balancing length L1. Simple. The second case, we have to find out the potential difference. So first, you have to find out the value of current. Current I equals E divided by capital R plus small r. Current I equals E divided by capital R plus small r. And then in the second, with the help of current, we can measure the potential difference across the resistors. V equals I into R, which is E by capital R plus small r into capital R. So this V is directly proportional to L2 now in the second case. So ER divided by R plus R is proportional to L2. And dividing these two expressions, 1 and 2, you will get small r is equal to L1 by L2 minus of 1 into capital R. With this, we can calculate the internal resistance of the cell. And if you look at this expression here, we can write, we look at the expression here, we can write look at the expression, it's very clear that small r is directly proportional to capital R. Also decrease. So the internal resistance of the cell depends upon the external resistance of the cell. The internal resistance of the cell is not a constant. The experiment can be repeated for different values of current. The experiment can be repeated for different values of current in the primary circuit. Though you are repeating for different values of current in the primary circuit, we can say the internal resistance R is not a constant. This must be clear. R is not a constant. R depends on capital R. As capital R increases, small r also increases. As capital R decreases, small r also decreases. Why? Why? We can check the diagram over here. If R is increased, if the resistance R is increased, the work that must be done by the source of EMF must be more. A large amount of work must be done. And that amount of energy will be obtained only from the active material of the cell. The energy will be obtained only by the active materials of the cell. If large amount of energy is consumed, active materials are mostly used up. If active materials are used more, the internal resistance gradually increases because the internal resistance is developed only because of the presence of active materials in an electrolyte of the cell. So as the active materials is increased more and more, the internal resistance of the cell will also be increased. See what happens here? As R increases, work done by the cell must be increased. Work done by the cell must increase. If work done increases, internal resistance R also increases. This is because of the creation of large number of active materials. Large number of active materials. So as R increases, capital R increases, small r will also increase. Internal resistance of the cell is not a constant. It all depends upon the external resistance of the cell. So this is all about the measurement of internal resistance of a cell using potentiometer. Idea is very simple. Only thing what you should know is that what is this L1, what is this L2. When we are measuring this balancing length L1, when the EK2 is open in the secondary circuit, when you consider the EMF of the cell. And then L2 is the balancing length of the potentiometer wire when the cell whose potential difference is considered, because key is closed, external resistance is included. So the EMF is not there. Instead, we'll be speaking about the potential difference. So L1 is for EMF and L2 is for potential difference. L2 is for potential difference. Here R is not included. Here R is included. R is included. This must be kept in mind. So with these formulas, we can simply calculate the internal resistance of the cell using potentiometer. Idea is quite simple. We shall now solve some of the problems related to the headings what we discussed. So you can learn something related to this one. So I'll read out the question so that you can understand it. I'll read out the question and then I'll solve the problem over here. Make a note of it so it will be helpful to understand the concept. Question number 1. While I was discussing about the introduction of potentiometer, I just told you which of the following device is meant for accurate measurement of EMF? Multimeter, voltmeter, voltmeter, potentiometer. It is potentiometer. So I'll write like this. Accurate measurement of EMF is done using potentiometer. Accurate measurement is done using potentiometer. Accurate measurement of EMF is done using potentiometer. Second question is, in a potentiometer of 1 meter length, an unknown EMF voltage source is balanced at 60 centimeter length of potentiometer wire, while a 3-volt battery is balanced at 45 centimeter length. Then the EMF of the unknown voltage sources. The potentiometer of 1 meter length. See, they have given a potentiometer of 1 meter length. L is 1 meter total length. An unknown EMF voltage source is balanced at 60 centimeter length of potentiometer wire. Let me show you the diagram. This is the battery, a key, a rheostat. This is connected to the terminal D. Now, an unknown source of EMF, V is unknown. Is balanced at 60 centimeter length of the potentiometer wire. This is balanced at a 60 centimeter length of the potentiometer. Balancing length L is 60 centimeter. Let me mark this as, for our understanding, I'm taking it as capital L. So you'll understand the difference between the two. Small L is the balancing length. L equals 60 centimeter. Into the potentiometer wire. While a 3-volt battery is balanced at 45 centimeter length. And they are saying for a cell of EMF, unknown EMF E, balancing length is 60 centimeter. And for a known voltage source of 3-volt battery, it is balanced against 40 centimeter length. See, they are connecting. So a known source of EMF balances the potentiometer wire. This is 3 volt and this is 45 centimeter. Let me say this is L2. We mark this as L1. L1. So for unknown EMF, balancing line this L1. For known EMF, balancing this is L2. You are asked to find out the unknown value of EMF. Unknown value of EMF. By comparison of EMFs of two given cells, we had the formula. E1 divided by E2 equals L1 divided by L2. In the first case, E1 is unknown. E2 is 3 volt. Balancing length L1 is 60 centimeter. Balancing length L2 is 45 centimeter. You can calculate E1 now. E1 divided by 3 is equal to 60 divided by 45. As the two are in centimeters, I can directly write it. So 4 divided by 3. So E1 equals 4 volt. E1 equals 4 volt. So you can have a clear idea over here. See, you can go directly to this question without solving the question. For 3 volts, it is 45 centimeter. So if the potential difference is 1 volt, what will be the balancing length? Hardly 15 centimeters. See, 15, 15, 15. So 15 for 1 volt, 15 for another volt, 15 for another volt. So 3 volt potential difference is balanced by 45 centimeters. So for 1 volt, it is 15 centimeters. So if you are getting a balancing length of 60 centimeter for an unknown source of EMF, then 60 is 4 multiplied by 15. So obviously we can say a 4 volt is balancing the balancing length of a potentiometer wire 60 centimeter. So the unknown source of EMF will be 4 volts. So directly we can go on with the calculation from the given data. Fine. This is E equals 4 volt. Then the next question is question number 3. A 2 volt battery, a 15 ohm resistor, and a potentiometer of 100 centimeter length all are connected in series. If the resistance of the potentiometer wire is 5 ohm, then the potential gradient of the potentiometer wire is. We are not speaking about the secondary circuit. What is gradient of potential? What is gradient in general? Anything that changes with respect to distance is termed gradient. Anything that changes with respect to distance is termed gradient. Potential gradient here refers to the change of potential with respect to distance. Velocity gradient, change of velocity with respect to distance. Anything which is referred to as gradient means that we are speaking about the physical quantity which is changing with respect to distance. So in mathematics and calculus, we can write it as d by dx, which indicates that something is changing with respect to the distance x. So a cell of 2 volt or a battery of 2 volt is connected to a resistor of 15 ohm, and then it is connected to a potentiometer wire of resistance 5 ohm. Potentiometer wire of resistance 5 ohm. The potentiometer wire is 100 meter long. 100 centimeter long. Sorry, 1 meter. That is 100 centimeter long. L is 100 centimeter. Total length of the potentiometer wire CD is 100 centimeter. They are asking you to calculate the potential gradient. Potential gradient. So here, when you are calculating potential gradient, you must calculate the potential drop across 1 centimeter. Potential gradient calculation must be done for 1 centimeter. What is the amount of voltage dropped across a length of 1 centimeter? So first we can calculate what is the potential difference across, or what is the current flowing through the circuit, and from which we can calculate the potential gradient here. So you are asked to calculate the potential gradient of the potentiometer wire. Potential gradient of the potentiometer wire. See, for the entire circuit, we can calculate the current. Current I equals V divided by R, total resistance. So I can write total resistance. Why I am writing total resistance? Because a 15 ohm resistance, external resistance is included, and a 5 ohm resistance, which corresponds to the potentiometer wire, is also there in the circuit. So I have to speak about the total resistance. So I equals V divided by R total. Potential is 2 volt. Resistance is the external resistance 15 ohm plus the resistance of the potentiometer 5 ohm. So we will have 2 divided by 20. This is 0.1 ampere. 0.1 ampere. So the current flowing through the circuit is 0.1 ampere. And this current flows through this 5 ohm resistance. What is the potential difference across the potentiometer wire? What is the potential difference across the potentiometer wire? This is what we have to calculate. So V is the total potential. Vp is the potential difference across the potentiometer wire. Vp equals I into Rp, where I is the current through the primary circuit. Rp is the resistance of the potentiometer wire. So simply we can write using the current 0.1 ampere. The resistance of potentiometer wire is 5 ohm. So this is 0.5 volt. So the potential difference across the potentiometer wire is 0.5 volt. The question is not complete. They are asking you still, what is the potential gradient? What is the potential gradient? Potential gradient here refers to potential difference across 1 centimeter of the potentiometer wire. So this is equal to the potential difference across the potentiometer wire divided by 100 centimeter. So that you will have 0.5 divided by 100 volt per centimeter. So this gives you 0.005 volt per centimeter. Is this clear? We call this as potential gradient. We call this as potential gradient. So what we did is that we first calculated the total current flowing through the circuit with the help of total potential and total resistance. So 2 divided by 20.1 ampere. Then what is the potential difference across the resistor? Means potentiometer wire alone. I can give you a clear picture still. If 0.1 ampere flows through the resistor of 5 ohm, and the voltage across the potentiometer wire is 0.5 volt. See, the voltage across the potentiometer wire is 0.5 volt. This is the value of potential across the potentiometer wire. What is the potential difference across the resistor R? Same current multiplied by resistance, 0.1 into 15 will give you 1.5 volt. So total potential V is VR plus Vp. So 1.5 plus 0.5 gives you 2 volt. This is the total potential. So total potential is divided out as 1.5 volt and 0.5 volt. This is what is shown. So this is total potential across the potentiometer wire. They are asking you to find out the potential gradient. So potential across 1 centimeter. So divided by 100 centimeters, total potential across the potentiometer wire divided by 100 centimeter gives you the potential difference across 1 centimeter of potentiometer wire. That will give you the potential gradient. So 0.005 volt per centimeter. Now, we shall go on to the next question. Question number 4. In an experiment to measure the internal resistance of a cell by potentiometer, it is found that the balance point is at a length of 2 meters when the cell is shunted by a 5 ohm resistance, and is at a length of 3 meters when the cell is shunted by 10 ohm resistance. The internal resistance of the cell is then. See, for all questions, we need to draw a diagram so that we will have a clear picture about it. A diagram is necessary. In an experiment to measure the internal resistance of the cell by potentiometer, it is found that Actually, this is the primary circuit. Kindly recall what we discussed. Primary circuit. Then SL of EM of E1 or SL of EM of E. Then an external resistor R and a key K2. Here it is given. It is found that the balancing point is at a length of 2 meters when the cell is shunted by 5 ohm resistance, which means we are including a 5 ohm resistance. And the cell is included with the 5 ohm resistance, the balancing length is 2 meters. Balancing length is 2 meters. Make it clear that the key K2 is closed, because of which we are speaking about the potential difference. We are speaking about the potential difference. It is no longer EMF. When you recall the content what we discussed in the measurement of internal resistance of the cell using potentiometer, we can make it very clear. When the cell of EMF is shunted with the 5 ohm, the balancing length is 2 meters. When it is shunted with the 10 ohm, the balancing length now becomes, this is exactly position J1, market J2, and the balancing length now becomes 3 meters. Balancing length now becomes 3 meters when the 10 ohm resistance is shunted. What is the internal resistance of the cell? What is the internal resistance of the cell? Actually, you know very well, the internal resistance of the cell can be calculated using the expression R equals L1 and L1 by L2 minus 1 into capital R. L1 by L2 minus 1 into capital R. Right. For the first case, I am writing for R equals 5 ohm, balancing length is a L2 is 2 meters. Why I am writing L2? Because we saw the formula R equals L1 divided by L2 minus of 1 into capital R. What is this L1? Balancing length corresponding to EMF. When R is excluded, but we are given condition R is shunted, means included. If it is included, we will have potential difference, and for that the balancing length is L2. So I am taking it as L2 equals 2. So small r can be written as L1 divided by 2 minus of 1 into 5 into 5. Then the second case, they have given R equals 10 ohm. The cell is shunted with a resistance 10 ohm. The balancing length corresponding to it is 3 meters. So small r will be L1, because L1 is not known, divided by 3 minus of 1 into 10. Is it clear? See, I am using the formula over here to determine the internal resistance. Actually, they have given first, when the cell is shunted with a resistance, external resistance R equals 5 ohm, the balancing length is 2 meters or 2 meters. And then when it is shunted with 10 ohm resistance, the balancing length is 3 meters. So with that, we have formulated two expressions. One is R equals L1 by 2 minus 1 into 5. And for the second one, R equals L1 by 3 minus of 1 into 10. As this R value is equal, we can calculate what is L1 now. What is L1 now? So we can write L1 divided by 2 minus of 1 into 5 is equal to L1 divided by 3 minus of 1 into 5. If you strike it out, you will have 2. So L1 divided by 2 minus of 1 is equal to 2L by 3 minus of 2. So I can write 2L by 3 or 2L1 by 3 minus of L1 by 2 is equal to 2 minus of 1. 2 minus of 1. So you cross multiply this, 4L1 minus of 3L1 divided by 6 equals 1. So L1 by 6 equals 1. L1 equals 6 centimeter. L1 equals 6 centimeter, where this is for pure EMF of cell, where R is excluded. So for pure EMF of the cell, L1 equals 6 centimeter. L1 equals 6 centimeter. Now, using this value of L1, we can find out the value of internal resistance of the cell. So we can write small r is equal to L1 by 2 minus of 1. L1 by 2 minus of 1 into 5. We can write 6 divided by 2 minus of 1 into 5. So 3 minus of 1 into 5. So 2 into 5. This is 10 ohm. In the other expression also, we will be getting the same result. R equals L1 divided by 3 minus 1 2. Then you will have you will have 6 divided by 3 minus of 1 into 10. So 2 minus of 1 into 10. So 1 into 10, 10 ohm. So internal resistance of the cell is 10 ohm. So this is a very simple and a clear idea to determine the value of internal resistance of the cell. Now we shall go on to another problem on the basis of comparison of EMFs of two cells. A potentiometer wire of length L and a resistance 10 ohm is connected in series with a battery of EMF 2.5 volt and a resistance in its primary circuit. The null point to a cell of EMF 1 volt is obtained at a distance L by 2. If the resistance in the primary circuit is doubled, then the position of the new null point will be. See? This is a simple problem, but will take some time. This is problem number 5, right? The potentiometer wire of length L. Potentiometer wire has a length L, and it has a resistance 10 ohm. Potentiometer wire has a resistance 10 ohm. This is connected to a battery of EMF 2.5 volt. Battery of EMF 2.5 volt and an external resistance R, which is unknown. This is unknown. This is closed. Some cell, a galvanometer, and high resistance. Let me see, jockey J. The cell of EMF E is equal to 1 volt. 1 volt. It balances the length as L by 2. The balancing length is L by 2. Balancing length is L by 2. Right. Now, if the external resistance or if the resistance in the primary circuit is doubled, then the position of the new null point will be. If this R is doubled, made 2R, what will be the new null point? This is the question. Is it clear? What will be the new null point? I can solve this problem simply. Let me first calculate the current and then potential gradient. First we calculate the value of current. I equals V divided by R. R total, V total. V total is 2.5 volts. R total is 10 ohm plus the resistance. Initially, the resistance is unknown, capital R. 2.5 by 10 plus R. This is the current. Then what is the potential difference? What is the potential difference across the balancing of the potentiometer wire? V equals I into R. So we can write here 2.5 divided by 10 plus R. This is resistance of potentiometer. So 2.5 divided by 10 plus R into RP. This is 2.5 divided by 10 plus R into 10 into 10. Now potential gradient. Potential gradient. So V for if the total potential across the potentiometer wire is divided by the total length of the potentiometer wire, we will be getting the potential difference across 1 meter. If a potentiometer wire is of length 10 meter, we have to calculate what is the potential difference across the length 1 meter. So potential gradient, V potential gradient, we can just show it differently. V potential gradient is potential difference across the potentiometer Vp divided by the length of the potential, divided by length of the potential. So we can write 2.5 divided by 10 plus R into 10 divided by L. This is the potential gradient. Potential gradient. 2.5 divided by 10 plus R into 10 divided by L. Is the potential gradient. So this is for 1 meter length. This is for 1 meter length. If we consider the balancing length for the potentiometer wire for a resistance R is L by 2, if the balancing length is L divided by 2, then we can write the expression as 2.5 into 10 divided by 10 plus R into L by 2 is equal to 1. Actually, we have calculated the potential gradient. Potential gradient multiplied by the balancing length L by 2 is equal to the EMF of the cell. That's the formula. This is of another form. E equals IRL. E equals IRL, where L is the balancing length. Here L by 2 is the balancing length. IR, where R is the resistance per unit length of the wire. See, I'll explain it clearly. E equals IRL. What is I into R? This is the total current. This is the resistance per unit length. What will you get? You will be getting potential per unit length into balancing length. So into balancing length. So potential per unit length is 2.5 divided by 10 plus R into 10 divided by L multiplied by balancing length L is L by 2. So I can write here 2.5 into 10 is 25 divided by 10 plus R into 1 by L into L by 2 into L by 2. This balances, or this is equal to EMF of the cell, which is 1. So L gets cancels out. 25 divided by 2 into 1 by 10 plus R equals 1. This is 12.5. So 10 plus R equals 12.5. R equals 2.5 ohm. R equals 2.5 ohm. The value of unknown resistance R is 2.5 ohm. Now, they are asking you to find out what will be the new balancing length if the resistance is doubled. If the resistance is doubled. So if R is doubled, then what will be the new balancing? What will be the new balance? So we can calculate the potential gradient here. We can calculate the potential gradient. New potential gradient is 2.5 divided by 10 plus 2R, because the resistance is double 2R into 1 by L is equal to 1. Is equal to 1. We haven't found the value of the EMF, so we can just keep it 2.5 divided by 10 plus 2R into 1 by L. This is equal to 2.5 divided by, this is 10 plus, sorry, 2.5 divided by 10 plus 2 into 2.5, because R has been determined as 2.5 into 10 divided by L. So 25 divided by 15. So this is 5 by 3L. 5 by 3L. So we have calculated the potential gradient as 5 divided by 3L. Now, what will be the new balancing length? New balancing length. I can write here 5 divided by 3L into X is equal to 1. So what is this actually? I don't know what is the balancing length. I am assuming balancing length as X. This is the potential gradient. Once again, the same calculation what I was shown. Potential gradient multiplied by balancing length equals the EMF of the same EMF of the cell is there. So it is 1. Same EMF of the cell is 1. So we have to find out what is the value of X. So X equals 3L divided by 5. So this is 0.6L. So balancing length 0.6L. Initially, the balancing length is 0.5L. Now, as the resistance R is doubled in the primary circuit, the balancing length increases, which is 0.1 times that of L, increases by 0.1 times. So X equals 0.6L. So this idea is very simple. What I am doing here, see, first you should understand what the problem is given. So they have given the potential difference, a resistor R is connected, and then the length of the potentiometer wire is, let us say, L. Resistance of the wire is, potentiometer wire is 10 ohm, and then this R is unknown. They are saying that the balancing length is L by 2 for the cell of EMF 1 volt. Now, when the resistance R is doubled, what will be the new balancing length? This is what is asked, and we have solved the problem over here. So first I calculated the current, then potential difference, then the potential gradient. Then this potential gradient multiplied with the balancing length is equal to the EMF of the cell, which R has been determined. New potential gradient must be calculated because the resistance in the primary circuit has been doubled. So with that, new potential gradient is 5 by 3L. Then the new balancing length is X. Potential gradient multiplied by balancing length is equal to the EMF of the cell, from which X can be calculated, which is 0.6. So we saw the comparison of EMF of the two given cells with the help of potentiometer, and also the determination of internal resistance of the cell using potentiometer, and the corresponding problems related to the idea what we discussed. So you just go through it, you'll have a clear picture about what we are talking about. This is all about today's session. We will be having the heating effect of electric current from tomorrow. Thank you. மறந்துட்டா நான் ஒரு மாதிரி டயர்டா இருந்துச்சு. எண்ட் ஆயிடுச்சா பாருப்பா.